Okay, new video for hypergeometric distributions. So this is 4.4 from the text, the last section of Unit 4. Let's talk about hypergeometric distributions and how they're different than binomial. The main thing is the events in hypergeometric are going to be dependent. So let me get things organized here. So you look here, we're talking about dependent events. So dependent events, they rely on the previous trial. Okay. So when we talk about dependent events, we always, not always, but usually when you're looking at cards. Okay. So cards and balls in a bag. Those are the ones that we've talked about in our class that are dependent events, not coins, not dice, right? Because trials in an independent event like coins and dice are not influenced by the previous result. So, for example, when you flip a head, the next guy can be a head or a tail. We don't. The first flip has nothing to do with it. When you take a spade out of a deck of cards, there are less spades left. When you take a brown ball out of a bag of brown and orange balls, there are less brown balls. Okay, so the next draw will have a different probability because it depends on what you get on the first draw. So those situations lead to hypergeometric distributions. The good news is we already kind of know all this. So what you're going to see are questions that are very similar to the probability questions for permutation and combinations. So examples: drawing cards, selecting balls from a bag, etc. We're looking at dependent trials, and we're looking for success. And we'll start off with a probability question. So from a full deck of cards, what's the probability in a 5-card hand will contain exactly 4? They contain the 4 of hearts. Okay, so we did this one here, the 4 of hearts. So you select the 4 of hearts. Remember how to do this, and then you select from the 51 other cards. You select 4 cards, and then overall you're choosing 52 out of 5 cards. Okay, so this is what you're doing. You're choosing 5 out of 52 cards. Sorry, I said that backwards. 5 out of 52 cards. And one of them is the 4 of hearts, and 4 of them are not that. So that's the probability of that happening. If you want to do this one different, and so again, we have success, number of success over number of trials. If we want to say exactly 4 hearts, so there are 13 hearts, and I'm choosing 4 of them, then I would also look at the non-hearts, and I would choose one of them. And then I'm going to have, again, 52, choose 5 as my denominator. So then you figure out what that is, throw in a calculator, and go from there. Okay, what's the likelihood that you randomly work 6 days a week, that you won't work on a weekend in February? So we know that there are 8 weeks in February. 8 weekends in February. There's 28 days. 4 weeks times 7 is 28 days. So that means there's 2 weekends, a Saturday and a Sunday each week. So that makes 8 weekend days. And the question is, if you randomly work 6 days, what is the probability that you do not work on a Sunday or a weekend, a Saturday or Sunday? So what we're doing here is we're not working at all. So 0 out of 8 days on the weekend, which means that we have to work 6 out of 20 days on the non-weekends or the weekdays, I guess. That's your numerator. Your denominator is just what's happening in general. What you're doing is you're choosing 6 of the 28 days to work. Figure out what that is as a decimal, and that's your answer there. Okay, so in general, this equation is quite huge. I wouldn't bother with it. Okay, so it's all here, but we know how to do this. So if we look at the question above here, what's happening is we have 8 successes, and we're choosing 0 of them. So here are all the definitions. I think this is one of these equations that unlike the last equation for binomials, I think this one is more complicated. Working with this equation than it is just doing the question the way we've done it before, right? Because you got Z's and you got N's and you got R's and all this stuff. I personally would never use this, okay? What I would do is I would look at the bottom and I would say, what am I doing? I'm choosing 6 out of 28 days. That would go here, okay? What's success? In this case, what am I looking to do here? Well, I'm trying to get 0 out of 8 days, and then that means I'm going to have 6 out of 20 other days. So this equation there, write it down if you'd like, but I'm going to pretty much ignore it as we move forward. This didn't photocopy properly, did it? Anyway, no, it didn't. Oh Okay, so I think I just photocopied every other page. Let's keep going though. Let's see what's going on here. Give me a second. I gotta pause this. Okay, so we're good. Just looking at this table here. It's quite extensive, quite long here. What you want to do, it's similar to the ones we did with binomials. Okay, the difference is this is a little bit. I think it's a little more work. Maybe it's not more work than the binomial equation. So what we're looking at is how many hearts you're going to get if you draw five cards. How many hearts are you expecting to have? What's the probability of getting 0 hearts, 1 heart, 2 heart, 3 heart, 4 heart, 5 heart? So for each of these, what you do, so I'm just going to use this one as an example here. In this case, I have 13 cards that are hearts, and I'm choosing 2 of them. So I want 2. What's the probability of getting 2 hearts? 13 choose 2. That leaves me 39 choose 3. So I'm choosing 2 of the hearts, 3 of the 39 non-hearts. Okay, that's your numerator. You can multiply those together, and then like every other question with cards, you're choosing 5 of the 52. Okay, put that in a calculator, you get 0.27. All these are similar. That's a 0. That's a 0. That means you're choosing 5 non-hearts. You're choosing 1 heart, 4 non-hearts. You're choosing 3 hearts, 2 non-hearts. You're choosing 4 hearts, 1 non-heart, all the way through. Okay, and each of these is put in a calculator. Don't round this to 0. Please give me an answer like that. And when you add them all up, you should get about 1. Okay, so when you sum up the px's here, you sum up the px's, it should be 1. The only reason it's not 1 is for rounding, okay, because it should be exactly 1 actually. And then for each of these, we're going to get the xpx's, and this will get us to where we want to go with the expected value. And what you do is you take this times this equals that. 1 times 41 equals 41. 2 times 27 equals 54. You add them all up, and you get here 1.25. Okay, so you're expecting to get 1.25 hearts when you draw 5 cards, which makes sense because that's a 1 in 4 chance of getting a heart each time. So if you have a 1 in 4 chance of getting a heart, that's a quarter chance. Do that 5 times, add them up, you have 5 quarters, 1.25. Okay, if we were to make a histogram for this, what you're going to do here for the histogram is you're going to go back and take these numbers here, 1, 2, 3, 4, 5. And when you do the histogram, please remember when you do a probability histogram, it's this column here. So you're going to plot these points here. So let me go up a bit, sorry. The 0 is 22, the 1 is 41, etc. The 0 is 22, the 1 is 41, etc. 27, all the way through. Okay, there's your histogram distribution. What's the probability of a flush of hearts, which is 5 hearts, that's just this. And the expected value from the table is 1.25. Okay, and that's that. The other thing you can do also is use this formula for expected value for hypogeometric. And what you do here, again, the formula might be a little more confusing than it needs to be. Now, if you went back to binomial, what you did for expected value is it was n times p, and n was the number of trials, okay, and p was the success rate. But it'd be the same thing here if you think about it, okay. So now the letters are all different. It's confusing. The n's down here, the r's here. But here's the question, okay? How many hearts are there? 13, okay. And what you want to do is you want to see how many hearts you get out of 5 cards. Okay, so there are 13 hearts, and what you're going to do is each time you're going to draw a heart, you have a 13 in 52 chance, or a 1 in 4 chance of getting a heart. So if you did that and said, okay, I'm going to do that, and I'm going to multiply by the number of times I draw a card, 5, it's 13 times 5 divided by 52, or 13 over 52 times 5. Okay, you can use the equation if you want. We have trials and success in total. Okay, so there's 5 trials here. We're doing 5 draws, right? You have success. There are 13 successes. That's the 13. It's hard to see. And there are 52 in total. And it's the same thing as what we just did. Okay, and you get 1.25. Okay, other examples here. These are really similar to what we did in the past. Okay, if you want to just get the even cards only, or no even cards, sorry. What's an even card? A 2, a 4, a 6, an 8, and a 10. Okay, so there's 4 of these, 4 of these, 4 of these, 4 of these, and 4 of these. That means there's 20 of them. Okay, and I'm not choosing any of them, which means I'm choosing 5 of the other 32. And this is what I end up getting. Okay, so that's that. And you can keep going through these examples. It's the same thing. 17 people in a class. We went through it. 8 have jobs. If I choose 8, what's probably that 4 will have a job. Okay, so in our class, we did this earlier. There's 17 kids currently in the class. 8 of them have jobs. Okay, so that means I'm choosing here 8 kids out of the 17. 8 out of 17. That's your denominator. Okay, that's what we're doing. But I want to have 4. I'm choosing. What's the probability that half of the 8 or 4 will have jobs? So half of the 8, so 4 of the 8 will have jobs. 4 of the non-jobbers are also being chosen. So I got the 4 of the people with jobs, 4 of the people with not jobs. Throw them in the calculator. That's really ugly. Hopefully you have these buttons on your calculator. You can just use those. Okay, and all the other questions are very similar. You're doing questions very similar to the ones we did in the past. Okay, so I don't think anything's that confusing. This one here, you can do or don't bother at this point, but take a look at it. The answer is 110, but you won't be tested on this. So let's just focus on testable material. Okay, so that's it. If you have any questions, ask. Otherwise, that's it. Have a nice day.